Shweta madam.
Which is left.
Good morning, Archana More madam. Can you hear me?
Yes, Shweta. Yeah, I can hear you.
How are you, madam?
Yeah, I'm good. And you changed that brochure? No, I saw it. Thanks. Are you able to hear me?
Yes, madam. Pardon me, I can't hear you properly.
Oh, hello. Maybe internet. Hello. Hello. No, I don't know what is the.
Good morning, Sujata madam.
Hello, good morning. Can you hear me?
Yes,
Hello.
madam, we can hear you.
So I wanted to test connecting my iPad and seeing if it works. Shall we do that?
Madam, we are quite lucky. And before, in 2016, you came to our college and we have listened to your lecture, madam. Again,
2016.
it's our,
Where did I come to? Can you remind me?
again, we are hearing your lecture today, madam.
Okay, I don't remember. Where did I come? 2016. Can you remind me? Hello? Hello? No, they can't hear me. Hello?
Hello.
Yeah.
Hello. I'm Oma.
I can't hear you. Your voice is bad. Yeah.
Hello. I'm seeing from the phone, so it's difficult.
Oh, okay.
The
All right.
instrument is bad. So
Okay. Yeah. Okay.
the only listening is okay, but speaking is not.
Okay, can you remind me this? Somebody said I came to your college in 2016.
There was an international conference at Reddy College. You may remember it as Reddy College, Narayanguda, Hyderabad.
Oh,
You
yes.
were
Yeah.
put
Okay.
in a guest house in NGRI, and
Right. Yeah. Now I remember that.
our head came all the way to the airport and picked you up.
Right. Now I remember.
You remember now?
Yeah.
Okay.
Yeah. Okay. Let me try connecting to my iPad. I want to check if that works.
Yeah.
Okay. So.
Yeah. Please.
Yeah. I'll share my screen. Tell me if you can see it now. Now you have to enable screen sharing for me.
She's on the phone.
Hello? Okay. Yeah. Okay. Now I can now share screen. Phone, iPad, via cable, share. Yeah. Can you see my screen now?
Oh, yes, we are able to see.
Okay, good. Okay. So, yeah. So let me know when we can start and I'll start. You can see the writing, right?
Yes, we can see it. Yeah.
Okay.
Madam, we will wait for 5 more minutes. At sharp 11 o'clock, we will start, madam.
Sure, yeah, no problem.
Okay, thank you, madam.
Hello.
Hello, yeah. Hello?
Madam, good morning.
Yeah,
Hello, madam. Hello, madam.
yeah, good morning, yeah. Can you hear me? I'm not able to get a clear picture of whether you can hear me, whether you can't, because your voice fades on the other side.
Madam, it's clear, madam. We
Okay.
can hear your voice as well as we can see the screen clearly, madam.
Okay, good. All right.
Okay.
So how many students are there in your course, math class?
Madam, it's almost 500 students, madam, in BSc as well as MSc, madam.
Ah, okay.
In 2019, madam,
Yeah.
we have started MSc Data Science, madam.
Oh, good. Okay.
MSc Data Science, so that in that each and every semester we have maths as well as stats papers, madam.
Right. So after this, after my lecture, can I talk to somebody? I think I spoke about it the last time when I was there. I'm trying to create school mathematics resources aligned to the NCERT syllabus, in English in the form of presentations, and also get it translated in as many Indian languages as possible so that teachers and students will benefit. So
Okay, madam, we will try.
so if your students or teachers can help me in the translation to Telugu, that will be very nice.
Okay, madam, we will be.
I will explain it to you. I'll write to you about it later. Okay.
Okay, madam.
Wow.
Good morning, everyone. I welcome you all for the second day of 1 week online international E-Symposium on modern mathematics. This celebrates Mariam Mirza Khan's birth anniversary. We are fortunate that Professor Sujata Ramdurai Madam is in India and can easily accept our invitation in spite of her busy schedule. Thank you, Madam, for accepting our invitation. And
Thank
now I call upon Bhargavi to introduce today's speaker for the third session, Professor Sujata Ramdurai Madam, to you all.
Good morning, everyone. I, Bhargavi, Assistant Professor of Mathematics Department, feel honored to welcome our research person, Sujata Ramdurai. Madam is an algebraic number theorist known for her work on Iwasawa theory. She is a professor of mathematics and Canada Research Chair at University of British Columbia, Canada. Madam worked as a professor at Tata Institute of Fundamental Research. Coming to the education, Madam awarded the PhD from Tata Institute of Fundamental Research under the supervision of Raman Parimala in 1992. Madam completed her Master of Science from Annamalai University in 1985 and Bachelor of Science from St. Joseph's College, Bangalore in 1982. Madam holds an adjunct professorship position at Indian Institute of Science Education and Research, Pune. Madam is a member of the scientific committee of several international research agencies such as the Indo-French Center for Promotion of Advanced Research, Banff International Research Station, and many more. Madam is presently a member of Prime Minister's Scientific Advisory Council from 2009 onwards, and also the member of National Innovation Council. Coming to the awards and honors, Madam became the first Indian to win the prestigious ICTP Ramanujan Prize in 2006. Madam also awarded the Shanti Swarup Bhatnagar Award, Krieger Nelson Prize for her exceptional contributions to mathematics. Let us welcome the most experienced and well-versatile professor in mathematics field, Professor Sujata Ramdurai. Madam, we welcome you and we are eagerly waiting for your valuable inputs. Thank you.
Thank you. Thank you for the kind invitation. I have a correction to make before I start on the mathematical lecture. I was a member of the National Innovation Council until 2014, and similarly of the Scientific Advisory to the Council to the Prime Minister. All this was until 2014. So that's something I should correct. All right, so now let's come to the mathematical topic of today. I'm going to talk about elliptic curves and arithmetic. So let's first focus on the first part, elliptic curves. And I want to convey to you that this has a very rich structure. And in fact, it has connections to different areas in mathematics, topology, geometry, and also number theory. And I'm going to focus on the number theory part. So let's define an elliptic curve first. And I'll use the following notation. Q is the field of rational numbers. And curves, usually these are what are called plane curves or planar curves. So geometrically, they are just solutions of equations. If you want to visualize them, then they are geometrically realizable as solutions of equations in two variables. And that's why they are called plane curves, because then if you plot them, you can actually see what they look like. So for instance, the simplest example is a circle, ellipse, and we know the equations for all of these. So for instance, for the circle of radius 1 with the center in the plane as the origin, it looks like this, right? This is the x coordinate, y coordinate, and this is unit 1 unit, and this is the origin. So if you plot the solutions, if you collect all the solutions of this equation, then what you get is a circle. Similarly, the ellipse, the parabola, you can view all of those as what are called conic sections, are another class of examples. But we are going to talk about something that's slightly different. So notice that these equations have degree 2 here, right? Both x and y are of degree 2. Whereas elliptic curves are going to be solutions if you want to understand the planar part of it. That is, if you want to plot them in the complex plane or in R2, then these are solutions of an equation of the form y squared equals f of x, where f of x is a polynomial of degree 3. So it's a cubic polynomial. And just to simplify matters, we will assume that it has distinct solutions. We know that it's a cubic polynomial, which means that the degree is 3. So therefore, if you want to solve for the cubic polynomial, we know that it has solutions, at most 3 solutions, and some of the solutions can repeat. And I'm going to assume that it's a cubic polynomial with distinct solutions. Okay. So one of the simplest examples, for instance, is you can take y squared equals x into x minus 1 into x plus 1. So this is just x into x squared minus 1, which is x cubed minus x. So as you can see, it has 3 distinct solutions, x equals 0, x equals 1, and x equals minus 1. And if you plot the solutions in the real plane in R2, so then of course, this is x coordinate 0 is one solution, then x equals 1 is another solution, and then x equals minus 1 is another solution. So it will look something like this. Okay. So the reason that we want this to have distinct solutions, so when we make this hypothesis, f of x has distinct solutions, will mean, what does it translate it to? Translates, to those of you who know some geometry, translates to the fact that the curve is smooth. So let me tell you what it means for a curve to be smooth. As you can see, for instance, again, if you take an ellipse, I'll draw some smooth curves for you so that intuitively you understand what is smooth. So this is smooth, it has no corners, right? This is an ellipse. Or if you take a circle, I mean, this is a perfect circle. Overlook the fact that, this should be really smooth, right? I'm not able to draw it properly on my iPad, but this is smooth. As opposed to something which is not smooth. Let me give you an example of something which is not smooth. Take a curve like this, or this one, y squared equals x cubed. These are also curves in the plane. Now these are not smooth. And why are they not smooth? So what happens is, if you look at any point on this ellipse or in this circle and take a small neighborhood in the plane, then the part of that circle which intersects intersect, it looks almost like a straight line. If I take a very small neighborhood, then it's almost like a straight line. So everywhere, anywhere on these curves, if I take a point and take a small neighborhood, then it looks like a straight line. Whereas that's not the case for this curve. For instance, if you magnify it and take a small neighborhood here, then it ends up around this point, it ends up looking like this. So this is what's called a singularity. This is a singular point, because it no more looks like a straight line. Similarly here, if I take this point and take a small neighborhood, so there it ends up looking like this. This is not a straight line. So these are non-singular, sorry, these are non-smooth. That is, these are called singular curves. So these are smooth. And these are non-smooth or non-singular. Sorry, singular. When it is non-smooth, we say singular. And the points where it is not smooth, they are called singularities. So now the reason for assuming that the elliptic curve has three distinct solutions, that is this f of x, the cubic has three distinct solutions, is when we plot it, then it actually gives a smooth curve. Now in geometry, the way to look at this is, you see, you look at this example again, x cubed minus x. This is not homogeneous, right? Because I'm just looking at its plane part. That's what is called the affine part. So this is an affine equation, and this is not homogeneous. What do we mean by homogeneous? Homogeneous means everything should have the same degree. Whereas here you look at this part, monomial, this has degree 2, this has degree 3, this has degree 1. Right? So they are not the same. So therefore it's not homogeneous. But if
afternoon 12 to 3 years 12 to 3
But if you want to make it homogeneous, you introduce another variable called the z variable, and then you add the z variable to everything to make it degree 3. So y squared z. Now this is 2 plus 1, so that becomes degree 3. X cubed, I don't need to do anything because it's already of degree 3. And now x is of degree 1, so I need to introduce a z square. So this is called projectivization or homogenization. Okay, so now you look at solutions. So you're going to look at solutions in 3 variables, x, y, z. And then they are usually denoted in this form because it's, so 2 solutions will be the same. If I take x1, y1, z1, I will then write that this is the same as multiplying it by a constant, lambda x1, lambda y1, lambda z1. So these 2 solutions will get identified. So that's because we are working in projective space in P2. Whereas here, when you don't introduce this variable and when it is not homogeneous, then you are working in what's called affine space. Okay, never mind those definitions, but this is a standard thing that we do in geometry. So now when we do this, then you immediately see that any elliptic curve has one solution. Okay, where x1, y1, z1, they're not all 0, not equal to 0, 0, 0. They cannot all 3 be identically 0. So these are the kind of solutions when you homogenize it. And once you do this, you see there's one solution that immediately stares you in the face. Namely, I look at 0, 0, 1, right? I put z equals 0, sorry, z equals 1, x equals 0, y equals 0. So that obviously satisfies this equation. And when I want to look at it in the affine part, I just divide. So if I have a solution x, y, z, then if I just want to remember the x and y, I will send it to x upon z because z is non-zero, let's say. Then you'll just look at the solution, y upon z. So that's how you get a projection into affine space, from projective space to affine space. Okay, so this is just the solution. So what this tells us is when we take an elliptic curve, then you always have one solution. And that solution usually is called, this is called the point at infinity. Why is it called the point at infinity? Because when you project it on the affine plane, you don't see this point. The Z coordinate is somewhere out there. So it's really somewhere out of the projective plane, out of the affine plane, out of the usual complex plane, right? Because the Z coordinate, the only part you see is here, but this point at infinity is really, you cannot see it in the affine plane. So that's why it's called the point at infinity. All right. So now these elliptic curves have amazing properties. And when it was first realized, which was sometime in the, already in the 15th, 16th century, I think, the Italian geometers and people knew about it. That's this amazing fact, which is you can add two solutions. So let's look at 2 points, y squared. So I'm going to, so remember for me, so therefore let me write. So when I talk of an elliptic curve, f can be any field, but we will largely work over f a field. But for us, mostly f will be either q, that is the field of rational numbers, or it will be the real numbers, the usual reals, or the complex numbers. So real numbers or complex numbers. And now you can ask for the solution. So you take y squared equals f of x. This is an elliptic curve. E over f is an elliptic curve. So f is either of those fields, f any of those fields above. And f of x is a cubic with 3 distinct solutions in. So f of x is a polynomial, cubic polynomial in this, with coefficients in this field. So that will be our definition of an elliptic curve, always bearing in mind. So you can look for solutions x, y, solutions E of f, solutions of this equation, plus the point at infinity. Remember, there's always this extra point at infinity, and we include that. So if we include all this, then what happens is something amazing, and that is the following. So I look at all the solutions, then this actually becomes a group, has a group structure. So what do we mean by this? In fact, it's an abelian group. What do we mean by it acquires a group structure? Remember, what are groups? It's just a set with an additive operation. If it's an abelian group, you will say an operation, binary operation, such that when you perform that operation on any 2 elements in the set, then what you get is again in the set, right? Example being Z, for instance. Z is a group because if I take any 2 integers and add them, Z is the group of ring of integers. So group, in fact, it's even a ring of integers. So I take any 2 integers, add them, that's again in Z, multiply them, that's again in Z. That's why it's a ring. Okay. But just group means there's one operation, and if you perform that operation on any 2 elements, you again land in that element. And every element has an inverse. And for instance, if I take any integer, then minus of that is the inverse, the additive inverse. When I add an element to the minus of that, then I get the special element 0, which is called the additive element, additive identity with respect to the additive operation. So E of f magically has a group structure. How are we going to define this group structure? It's not something naive. So I can take 2 solutions, x1, y1, and then I'll take another solution, x2, y2. So you should think of these as points. So let this be a point P1, and this is a point P2 on the curve. And this is not the same as adding these two. P1 plus P2 is not equal to adding the coordinates x1 plus x2, y1 plus y2. It's not something as simple as that. And defining the group structure uses geometry. And I'll explain to you how. And again, it's really miraculous that people saw this. It's coordinate geometry, but a little involved. You cannot teach it. For instance, you all learn coordinate geometry, equation of a line and line intersecting a plane and all of that. in linear algebra or in coordinate geometry. It's not something that can be taught at that level. Maybe you can teach it at BSc level, and so that's why it's amazing that mathematicians discovered it a long time ago, And how do we define the group structure? So to define the group structure, use the following fact. So take a line in the plane. Let's work over R2. That is, let's work over R. The same argument, you can make the argument algebraic and you can see that that argument works over any field. But in order to keep it also visual, that is, in order to enable us to see what's happening, let's work over R. So any line, I'll just say any line. So what is the degree of a line? So line, that's why it's called a line. It's a linear equation. Linear means degree 1. So roughly you should think of it as some equation where everything occurs in degree 1, right? For instance, equation of a line, in coordinate geometry is ax plus by equals c, where a, b, c are constants in the field. So that's a line in that field. Now let's take this elliptic curve, and I mentioned that in elliptic curve, you have this f of x. This is a cubic, so which means it has degree 3. Okay, so the basic idea, this is called Bezout's theorem in algebraic geometry, and I'm not being very precise here, but roughly it says what happens when you take, says the following. Suppose I have an equation f of x, f equation in degree m. So I really should be precise here, then I should say it's a homogeneous equation. But remember, I mentioned you can always go from given any equation, you can homogenize it introducing an extra variable. Okay, so suppose it's an equation in degree m, and then I have another equation g, which is an equation in degree n. Now you can ask for what are the simultaneous solutions of both of this. So I take all the solutions of f, I take the solutions of g, and then I can ask what is the chance of finding a solution which satisfies both f and g. That's defined by the intersection of f and g, right? That gives the common solutions for both f and g. And Bezout's theorem says that if I take an equation f in degree m and an equation g in degree n, then they intersect has at least m times n elements. Okay, so for instance, in this special case, we are taking an equation which is a line, so that's degree 1, and then elliptic curve, which is degree 3. So if Bezout's theorem, if we apply Bezout's theorem here, the two of them should intersect in 3 points, counted properly. Okay, so now let us see what this means. So I want to add 2 elements. So for instance, again, I'll take an elliptic curve. Suppose it looks like this. This is a degree cubic equation. For instance, one of the examples look like this, where the 0 y squared equals x cubed minus x. This is a slightly different curve, but it again has 3 equations with x on the x coordinate on x equals 0. Sorry, with y equals 0. So now if I take 2 points on this and I want to add them, this is a solution, this is a solution, and I want to add these two, then what I do is I connect these two by a line in the plane. So now this is a line, and so this is of degree 1, and then you have an equation of degree 3. Elliptic curve is an equation of degree 3. So therefore, these two, there are 3 points of intersection. One is these 2 points. You already have 2 points here. Plus there is a third point. Okay. We don't know where that is, but there is a third point. So there is a third point of intersection. Okay. So in other words, take 2 points P and Q on the elliptic curve. And I want to define what is P plus Q. Let me put P this to denote the group operation. How do we get P plus Q? So in order to do that, first join P and Q by a line. This you can do because in the plane, given any 2 points, you know the equation for the line joining those 2 points. Join P and Q by a line. So you get a straight line. And that straight line, because it's of degree 1, it's going to, let's call that L. Okay. Now the line L, because it has degree 1, and intersects the elliptic curve E, which is of degree 3. When I say E, I'm thinking of the f of x, which is a cubic. Intersects E, which is f. I'm looking at the cubic part, so which has degree 3 in 3 points. Of these 3 points, I already know 2 of them. 2 of them are P and Q. PQ. Now, whatever the third point is, what you do is then you join. Remember, there is a special point. Join the point at infinity. Remember, point at infinity was the special point. 0, 1, 0. Okay. Join the point at infinity to the third point. Let's call it R. And okay. So now again I get a line. So call this line LP plus Q or LPQ. So how have we got this line? We first join P and Q. Now that line already intersects the curve in 2 points, and then it's intersecting it at a third point. And whatever the third point is, think of the point at infinity somewhere up there, join that point at infinity to the third point. So again, you get a line. That line is intersecting this curve in 2 points, namely at infinity and this third point R. So now this LPQ intersects the curve at 3 points again by Bezout's theorem. And 2 of them are already the point itself, infinity, point at infinity, and R. So that third point is what is P direct sum Q. So this is a geometric way of defining the addition, but you can explain all this can be made very precise, using algebra and coordinate geometry. Okay, coordinate geometry. And so this will give you, so if I take P, so suppose we have y squared equals f of x, where f of x is in some field, right? F of x, where I said for convenience, I'm going to work with f equals q, r, or the complex numbers. But this is in general, you can work with any field f, and this is a cubic over f. Then when you do this process, so f of x looks like, typically it look like, x cubed, we can, let's say top coordinate is of degree is mnemonic. So it look like x cubed plus ax squared plus bx plus c, right? This is a typical cubic where a, b, c are in the field f. Now what you can do is, if I take a point P, which is x1, y1, z1, and Q, which is x2, y2, z2, then can express P plus Q as a point x3, y3, z3, where all of these x3, y3, z3 are expressed. They are polynomial equations, polynomial with denominators, or rational equations expressed in terms of functions of x1, y1, z1, x2, y2, z2, and these coefficients. X2, y2, z2, and the coefficients a, b, c. Okay, so everything, this expression for p plus q, so you can see that this again lies in, so all these points. So when you do this, hence x3, y3, z3, this is an element in f, f3, 3 copies of f. What I mean is, if I take x1, y1, z1, all of these are in f, x2, y2, z2, they are all in f. Then when I add them, I get x3, y3, z3, which is again, all 3 coordinates are in f. So therefore, on the solution set, we have defined an addition, and you can also define the inverse. So for example, in this simple example, the negative of this point will be this point. Okay, so you can actually give an algebraic expression for the addition of 2 points. All right, so now it is an abelian group. So that's the first theorem. So theorem, E over F is an elliptic curve. Then when I look at the solutions E of F, this is an abelian group. So remember, once it's an abelian group, you can talk about the structure theorem for abelian groups. Structure theorem for abelian groups says the following. So if I take any G is a finitely generated abelian group. So which means as a group, it can be generated by finitely many elements. G, a finitely generated abelian group. Then G can really be thought of. So G is the same as, this is isomorphic in the language of groups. So G has a free part. So there are certain copies of the integers ZR plus a finite group. And further, you can understand the finite group. The finite group also looks like some direct sum Z mod P. You know, it has a P torsion part. So P I N I, direct sum Z mod Q I N I, Q J M J, so on for finitely many primes. LK, PK. So these PI, QJ, these are all primes. PI, in fact, let me not write PI. Let me just write a single prime. So this is P, this is Q, and this is L. And these direct sum is outside. So this is a direct sum over K, right? So P, Q, L are primes. So it really looks like cyclic groups. Finite, the finite part looks like a direct sum of cyclic groups. Let me give you a simple example. For instance, you can take something like Z, direct sum Z mod 2, direct sum Z mod 3, direct sum Z mod 9, right? 9 is 3 squared. So you have the part corresponding to the prime 2 is this, the part corresponding to the prime 3 is this, and so on. So it says this is a finite sum. Each of these, the number of primes that occur are finite, and also the number of summons, each prime, for each prime, there are only finitely many summons. So therefore, this whole thing becomes a finite group. So this is an amazing theorem, structure theorem for finitely generated abelian groups. So right now we have only said that E of F is an abelian group, right? But again, the remarkable theorem, this is due to Model. So an 18th century mathematician. In fact, this year is 100 years since he proved the theorem. So there's a conference called 100 Years of Model. So he proved the theorem that if I take an elliptic curve E over the field of rational numbers, then I look at the solutions, E of Q. I know that it is an abelian group, but there is more you can see. E of Q is a finitely generated abelian group. Why am I putting an exclamation mark? Because it's a very neat theorem. It says it's finitely generated. So if I have an elliptic curve E over Q, then I can look at the points E of Q, and then I can use the structure theorem. So from the structure theorem, I get the rank R, which is the rank of E. This is called the rank of the elliptic curve. That is the number of copies of Z that's here in the structure theorem, this R. Okay. That's called the rank of the elliptic curve. And then there is the torsion part. And then you can ask, so what is the rank? Given an elliptic curve, can I find the rank? How big can the rank be? And so on. So these are all very important questions. A lot is known, but it's beyond the scope of this lecture to tell you. But this is a very active area of research. And you can understand how important it is if even after 100 years, people are still trying to understand the structure of elliptic curve, points of an elliptic curve. Now, this is important that it's over Q, because such a statement is not true over any field. For example, if I take F equals the complex numbers. So complex numbers, field of complex numbers. And then again, you look at E of F. E over F is an elliptic curve over the complex numbers. Then I look at E of F. I look at the solutions here. Now it's definitely not true. This is not, so I'm going to write E of C because I'm looking at the complex numbers. This is not a finitely generated abelian group. It's an abelian group, but it's not finitely generated. So what does it look like as a group, as an abelian group? So the simplest way to think of the points of an elliptic curve, if you want to think of it rationally, that's where topology comes in. If you want to understand this, then studying elliptic curves over complex numbers is related to studying complex manifolds. You'll be hearing a few others talk about this, studying complex manifolds, and also related to topology. And this is where Mirzakhani's work comes in. In fact, elliptic curves, when you look at it over complex numbers, it's a rather simple object. Of course, when you're thinking of a curve over the complex numbers, that means somehow curves always have dimension 1, right? So this is a complex object. This is a curve of dimension 1 over the complex numbers. But remember, linear algebra, complex numbers have dimension 2 over the real numbers. So over the reals, an elliptic curve really becomes a surface over the reals. And what do they look like? So when you think of them as the real surface, then it really looks like a torus. And how do you get this torus? So you can think of complex numbers. So this is the complex numbers. Inside the complex numbers, you fix a lattice. That is, you fix a two-dimensional subspace, a basis. See, remember C over R, linear algebra tells you this is two-dimensional as a vector space. So you can choose two real vectors which generate it. For instance, you should always choose one which is, let's say the simplest case will be choosing this unit vector on the x-axis and the y-axis. But you can choose any two generators. But when I choose that, then this forms a lattice. So I can take all these lattice points. It goes on, right? These are the lattice points. So let me look at this smallest lattice. So how you get this complex manifold or the elliptic curve is you look at this parallelogram here. So just this part. So let me just look at this lattice here. This is all square. Then what you're doing is you're identifying this and this. Let me use different colors for the parts I'm identifying. So I identify this and this. So what does this mean? You take a square, you're identifying the two sides. Then it becomes a cylinder, right? I take a square, I identify these two, then I get a cylinder. But I need to further identify these two. So those two have now become this part and this part. So I need to identify that. And when I identify that, you get a torus. This is called a torus. So this is in some sense the simplest complex elliptic curve, which has a complex object manifold, which has a group structure. And then of course you can see that, you know, it has a curvature. You can study so many different topology related to the topology of the surface. Much of it is what related to work of Mirzakhani, she did not just stop at these simple surfaces. She studied many more complex surfaces, and that gives rise to what's called differential geometry. And I noticed that in your lectures, you're also going to hear others talk about some aspects of this work. So this is how elliptic curves enters different areas in mathematics. For instance, algebraic geometry, complex manifolds, algebraic topology. But more importantly, I mentioned how you add 2 points on an elliptic curve. There is this complex operation that you perform, joining the 2 points, then intersecting the third point with a point at infinity, joining those two, and then intersecting it with the curve again. And all this can be made algebraic. In fact, you can also implement it on a computer. And that's a very complex operation, but you can codify it. And that's the reason that you see the use of elliptic curves in cryptography. Okay, so elliptic curves come equipped with mathematical operations which you can explain in algorithms, operations, algorithmic. So I will just write algorithmic, by which I mean you can actually say what you have to do step by step, even to a computer. That are two ways. That is, when you think of it as function, you go back and forth. So for instance, you can add, subtract, right? That are two-way operations. One way is easy, meaning not too difficult to codify, but the other way is difficult. So let me give you one example of such an operation. So for instance, multiplication. So you can multiply any two large numbers. Today, in fact, your mobile phone can do it. You take two very large numbers, your mobile phone can multiply two large numbers in a fraction of a second. But your mobile phone cannot perform the reverse operation. What is the reverse operation of multiplication? It's factorization. And there are no computers strong enough to factorize a big number. There is no universal algorithm which can factor a large number and find a prime factor for that large number. So this is at the basis of all your internet transactions. You know, internet banking, internet cryptography, all of this simple fact that multiplication and factorization or inverse operations, multiplication is easy, factoring is difficult. That is what is used in the heart of cryptography. And elliptic curves have a lot of such complex operation, two-way operations. One way is easy and the other way is difficult. So that's why they're useful. So this is the basis for what's called elliptic curve cryptography. You'll again hear a lecture about that. Okay, so I hope I have convinced you that, I should tell you why E of C, the elliptic curves, the complex number part, So E of C, when I look at the complex points, this operation, when you translate it algebraically and arithmetically, this is, I'm again not being, so this you can see, this gives rise to a group. So for instance, it really looks like, I just put this in inverted commas, it looks like Q mod. So what is this? So it looks like two copies of R mod Z cross R mod Z, this torus, right? So I look at this complex numbers, or let me write the real numbers. So I can think of this torus. So let me call this E. If I want to think of it as a group, then I can also think of it as R mod Z, R mod Z. Because what you have really done, this object, this operation of taking a square, identifying the lattice point. So you have identified this lattice point with this lattice point, and this one with this one. And so let me again color code. So when we have made the identification, this point gets identified with this point. And then all these points have got identified. So that means all the integers have collapsed in the real line. If you think of the real number line, and you're doing it twice, once across the x-axis, once across the y-axis. So the points really look like R mod Z, direct sum R mod Z, and this is really not finitely generated. You cannot generate it. Okay. So this gives a reason. So this, well, again, I'm not being precise here. So looks like this, and E of C is not finitely generated. This is not finitely generated as an abelian group. So I have indicated to you how elliptic curves show up in number theory. How does it show up in number theory? Because you want to understand the rank of an elliptic curve. When you study objects over Q, they are closely related to arithmetic. That's closely related to number theory. So in understanding the rank, so this is where number theoretic methods come up. When you want to study them over the complex numbers or the real numbers, that's where manifolds and topology comes in, algebraic topology. And then when you want to use it in cryptography, so again, because they come equipped with these mathematical operations, you study them in cryptography. So elliptic curves are really very structural objects. They're objects with a rich structure with connections to different areas of mathematics. And it leads naturally to many other higher dimensional objects. This is dimension 1 because it's a curve. So you should think of it as dimension 1. They are higher dimensional objects where the solutions have an additive structure, have a group structure. Those are called abelian varieties. Those are of higher dimension. And then in turn, they are related to modular forms. They are related to so many different objects. And of course, Fermat's last theorem, that was one of the most famous problems, open problems, which roughly said that you look at this curve, x to the power n plus y to the power n equals z to the power n. This has integer solutions. Solution, if x, y, z is an integer solution of the form, implies then if and only if one of them is 0. X or y or z has to be 0. So this is Fermat's conjecture, right? Which was made in the 18th century. Fermat's conjecture. And of course, we all know this was proved around 2000 in the last century, late 20th century, last decade of the 20th century. This was finally proved by Andrew Wiles. And this is really a theorem which brings together, this theorem brings together all the different aspects of study of elliptic curves, brings together different aspects of the study of elliptic curves. So this is for n greater than or equal to 3. For n equals 2, of course, that's a square, sorry, that's a circle and it has x squared plus y squared equals z squared, that has infinitely many integer solutions. Whereas for degree greater than 2, it has only finitely many solutions. Aspects of the structure of elliptic curves. So this continues to be a fascinating area of research, and I hope I have introduced to you some aspects of the importance of the study of elliptic curves. So I'll stop here and I'll take questions if there are any questions. Thank you for your patient listening. Okay, I'm done. So if there are questions, I'll be happy to answer questions. Hello?
Can I ask one question?
Sure. Yeah.
So when you take this elective curves over Q and so on, solutions to lie again inside Q, you may need to do something, like Bezo's theorem, for instance.
Exactly. That's what I said in the beginning, right? All this, I explained to you how you add two elements. I explained to you by geometry what is the principle involved. But then I also said that you can make this precise. Here I've said can be made precise using algebra and coordinate geometry. So for instance, think of it this way. You take 2 points. Let's take x, y, p and q, where x1, y1, z1, x2, y2, z2. These are all irrational numbers. Now, when you add them, what do you do? The first thing you do is take a line joining p and q.
Yes. That is
now, that will again have coefficients in q.
Yeah, that is.
Now, and then you're taking the elliptic curve, which has coefficients in q, and you're finding the intersection.
No, I call you from here.
Right? So that again will have, that point will again lie over Q.
Yes, that is correct. Huh?
So then again, now I'm taking that point and joining it to
the
point at infinity, which again has coordinates in Q.
Okay, 0, 0, 1, that point.
Yes.
Yeah.
So that line again has coefficients in Q.
Okay.
And now that will intersect the elliptic curve, which again has coefficients in Q. So that third point of intersection will again have coefficients in Q. But to make that precise, to write, I didn't write that complicated formula here.
No need. Yeah, I just wanted to see, because we generally teach Bezo's theorem over complex. So there, everything is algebraically close. So everything lies inside C. I mean, we don't need to say.
No, but here you can really do it with your bare hands. You can write the equation. It's a little tedious to do it, but you can do it.
Okay. Yeah. Thanks, sir.
Okay. Yeah. Okay. Are there any other questions?
Thank you, madam, for giving a nice lecture on elliptic curves and arithmetic. Now I ask Bhargavi to give vote of thanks.
Thank you, madam. Good afternoon to everyone. It is a great honor to propose vote of thanks. I thank Professor Sujata Ramdorai, madam, for giving her valuable inputs on elliptical curves and arithmetic, and how the points on the elliptic curves forms an abelian group on rational numbers, model theorem, and it is not true for complex numbers, and how the arithmetic on elliptic curves is being used in cryptography. It is my pleasure to thank Professor G. Sudarshan Reddy, Secretary cum Correspondent, for conducting the session on elliptic curves and arithmetic. I would also like to express deep gratitude to our principal, Dr. J. Achyuta Devi ma'am, our vice principal, Dr. Kavita ma'am, and head of the department, Mathematics and Statistics, Shweta ma'am. I thank one and all. Thank you.
Yeah, thank you. Who should I write to about this online resources that I'm trying to create and for which I need help in translation?
You can write to me, Uma, or Shweta.
All right. Okay, I'll do
Any
that.
of us.
Yeah, thank you.
Thank you so much.
Yeah, thank
It's
you.
been a pleasure.
Yeah, thank you. Bye.
Thank you everyone for attending this session. We'll again meet for the next session at 4 p.m. Today by Professor Shanta Lashram, Sir, on arithmetic of binary recurrence sequences. Thank you one and all.